our work. All right, guys. So, yep. So as you know, this is the fifth webinar we have, fifth session of design validation webinar conducted by Intercad, which we aim to assist designer and engineers to utilize their simulation, the simulation tool in their daily activities. We are organizing a series of seminars to present the capability of the software in various applications. It is a very great opportunity to have a face-to-face meeting with our valuable prospects and customer to understand their specific simulation needs. The first seminar, as you can see in the presentation, is conducted by Intercad on 26th of September in Melbourne, where you can also ask for the registration link. If you haven't registered yet, just send us an email and we will provide the registration link for you as soon as possible. And also we're planning to have more of this type of webinar seminars through the different states if it is more people are interested, and we can organize that. All right, let's start our work today, where the topics we are covering today is first talking about basic of heat transfer and energy transfer. We simply defining what does it mean, how does it formulated. Then we will have a brief interview about heat transfer mechanism, which is conduction, convection, and radiation. We have we will present the main formula and how we treating these problems in general to give an idea, to have an idea about what parameters are important when we have this mechanism. Then we will bring this to a real case study of a microchip, where we're trying to show you how we create a thermal analysis in SolidWorks, and we will have 4 different cases on, or 4 different study on this assembly, where we first considering the steady state heat transfer, and then we will have 2 transient thermal analysis where we have a single step heat load and multi-step heat load, and at the end we will show you the option exists in SolidWorks simulation where we can control the heat generation by putting a thermostat option on our model. And also at the end we will present the capabilities of SolidWorks simulation and introducing different seats we have available in SolidWorks simulation. Now, as an engineer, we are interested to see the equilibrium state of our, let's say, environment, our product, our design. And this is also always concerning about the energy balance of the system. If we have a closed system, energy can be transferred to or from a given mass by 2 mechanisms. One could be heat transfer and the other could be work. Note that if we have an open system, mass could also bring the energy in and out. So our job is to find the equilibrium state by saying how much energy coming in, how much energy going out, and how the energy of the system is changed, and if the system is in equilibrium state. Now, because today's webinar is about heat transfer, let's focus on one of the mechanisms, where we're defining heat as the form of energy that can be transferred from one system to another as a result of temperature difference. It's denoted by Q and could be measured by joule, kilojoule, or calorie. Specifically, transfer deals with the system that have lack of thermal equilibrium, and thus it is a non-thermal equilibrium phenomenon. This study will consider how long does it take from the current state to reach to equilibrium state. And do not forget, the main driving force for heat transfer is temperature difference. If we would like to compare the thermal analysis or heat transfer analysis to a structural analysis, we can simply resemble these two studies, as both of them, they are talking about equilibrium state under an applied load. These loading or measure or constant are very similar to each other, as we have listed in the table, as you can see here. Displacement look like a temperature. Strain look like temperature gradient. Stress could be resembled as heat flux. Load as heat source or heat sink. Prescribed displacement as prescribed temperatures. And elastic support could be resembled with convection coefficients or field coefficients. And elastic modulus look like thermal conductivity. So as you may be more experienced in the structural analysis, where you have a system undergo to a equilibrium state under applying a load, and these are the measure, this is exactly the same when we're having heat transfer analysis. Loads, measures, and constants. All right. Let's focus more on heat transfer. Based on the second law of thermodynamics, heat transfer in a direction to decrease the temperature. And this rate of heat transfer in a certain direction is highly dependent on magnitude of temperature gradient in that direction. Therefore, if you have larger temperature gradient or temperature difference, you will have higher rate of heat transfer. So that is the basic law and make a lot of sense, and you observing in your daily activities. We also have some let's say terminologies in this area of the study, that the amount of heat transfer per unit time is called heat transfer rate. So basically, rate means per time, and we denote it by Q dot. But if we have interested to see the heat transfer rate per unit area normal to the direction of heat transfer, we call this heat flux. So we simply denote it by small q and a dot on top, where it is Q dot, big Q dot, over the cross-sectional area normal to heat transfer direction. So these are the basic terminology, and you shouldn't be confused before doing anything, any studies. Heat transfer rate, and heat flux. All of what we're doing in analyze the system from its non-equilibrium state to equilibrium state, as we said, it is based on energy equation. The first law of thermodynamics simply it's stating that energy can neither be created nor be destroyed during a process, just it can only change the form. Or we can say the total amount of energy entering system minus the total energy leaving the system could change, it will equal to the change in total energy of the system. Or if we're denoting it by symbols, we can say energy in minus energy out, where this energy could be in a form of heat, work, or mass transfer, will change the rate of internal, kinetic, or potential energy of a system. Simply, you're putting an entry and you will have the effect, cause and effect. Heat transfer, then internal energy change. You putting work, it will displace. For example, it's getting evaluated. So that is the general rule, but if we simply focusing on heat transfer in specific, and the only mechanism of heat energy transfer would be heat, this energy could be rewritten, energy equation could be rewritten by saying Q in minus Q out, net heat transfer, plus energy generation, such as element or anything else within your system that generates energy or outsourcing the energy in, will equal to the change of thermal energy of the system. So this is the equilibrium state that analytically or numerically we're trying to achieve. We're getting some input such as temperature difference, heat, work, or mass. Then we bring it their effects, and we analyzing its effect about how it is changing. Is it displacing? So we're talking about structural mechanics. Is it moving? We are talking about, let's say, dynamics. If the temperature changing or internal energy changing, we're talking about heat transfer and thermodynamics. Therefore, there are all subcategories of energy equation where we simply concentrating on the some mechanism of heat energy transfer and some specific effect of it. Okay, then let's focus on the mechanism of heat transfer here. Heat can be transferred in three basic modes. If we're talking about heat transfer between solid bodies, such as you can see, we have a pan over a stove, this mechanism is called conduction. So solid to solid heat transfer is called conduction. But if we concern about heat transfer through the fluid which interacts with a solid body, that mechanism is convection. As you can see, the pan is on the stove and the temperature distribution through the water level is through convection, as it's in contact with the pan surface. And the last category is talking about heat transfer radiation, which is the heat transfer by electromagnetic waves from a hot surface to this environment. All right, so we can have any of these, and more realistically, all of these three, let's say, mechanism mostly will occur in our daily activities. Now, let's focus on each of them individually and see what sort of formulation we have for this. The first category, let's introduce conduction. The transfer of energy from more energetic particles of a substance to the adjacent less energetic ones as a result of interaction between particles. So through a solid domain, through a substance, less energetic particles will hit more energetic particles will hit less energetic particle, and they will transfer their energy. So this is a very macroscopic, let's say, observation, but this is how it's getting transferred, so in a macro scale. But let's imagine we have a plain wall, as you can see here in the picture, with a thickness of delta X, isothermal surface temperature of T1 and T2, where we're expecting if T1 is more than T2, heat transfer of Q will go in that way. We have the same surface area here on phase 1 and phase 2. Therefore, we can state that rate of heat transfer conduction is proportional to area, temperature difference, and thickness. Or by other word, we can bring this proportionality to equality by saying Q conduction equal to a constant, which we call this constant as thermal conductivity, times cross-sectional area. As you can see, it's normal to heat transfer direction, temperature difference, and length. But one very important fact here is because T1 and T2 over the surface are simply constants, we can write this equation in that form. If they are not, then in a differential form, or Fourier first law of heat conduction should be written, where we're looking for K as thermal conductivity, area heat transfer, area of heat transfer, and gradients of temperature over the lengths. So this is how we can formalize the heat transfer conduction, and the main property here we introduce is thermal conductivity. Now let's have a look through this property. The thermal conductivity of a material is a measure of the ability of the material to conduct heat. Therefore, it is a property of a material. If we have very high values, then we have a very good heat conductor. If we have low values, we have poor heat conductor or isolator. Here is some figure for comparing the different material. The best insulator look like we have foams, and the best conductors is like some metals such as zinc and silver. All right, let's move to the next mechanism of heat transfer, which we call it convection. Convection is the mode of energy transfer between a solid surface and a just liquid or gas that is in motion. So we're talking about the interaction of solid and fluid. So basically, it is a conduction mechanism plus a fluid motion. We usually classify three categories in convection. First, if you have a hot solid phase through the fluid domain, which could be an air, such as hot egg through environmental, let's say, atmosphere, and we have natural convection. If we're using any external force to move the fluid over our solid domain, which we call it force convection, we have different, let's say, formulation about this, and we treat this problem differently. And we have the last mechanism where it's talking about change of phase from liquid, vapor, solid, and etc. So all of these three classification is talking about convection, where we have a contact of solid to a fluid. How we formulate this? It is very well-known equation of Newton's law of cooling, which is stating that Q dot convection is a constant called H, which is convection heat transfer coefficient or film coefficient, multiplied by cross-sectional area normal to heat transfer direction, surface temperature, and fluid temperature. Very important note, in contrast with K, H is not a property of the fluid. It really depends on surface geometry factor, nature of the fluid motion, properties of the fluid, and bulk fluid velocity. Therefore, a very close analysis of the fluid motion around our solid is playing an important role to, let's say, estimating the H value. More turbulent flow, we have better H values. Less energetic, we're getting lower magnitude of H. So it could be very complicated when you're trying to estimate the H values. There are a lot of reference to get the appropriate formulation in a different flow regime, in different flows, let's say, geometrical factors. However, this table, as you can see here, it's showing you a very rough estimation and a guide about the H value. But be very aware of, if you have a very complex shape or you have no idea about, let's say, the fluid regime, using any values of H coefficient of heat transfer convection could end up with a very wrong result. Okay, so one extra note when we would like to introduce here, if we have two solid domains with different, let's say, surface flatness or roughness or contact, then we have two mechanism of heat transfer, conduction and convection between the solids. As you can see, we have air gaps here. In this case, we have to present a thermal resistance, which is the resistance to heat flow at the junction of two components caused by tiny air gap due to the roughness of the surface in contact. That's simply defining as U, which is the reverse of heat transfer coefficient or film coefficient, which is L over Ka. There are some prescribed values about the typical joints we have. However, if you need more accurate of this material, these values, you have to go to the right reference books and find this value more appropriately. And now let's move to the last mechanism of heat transfer, which is radiation. Simply, radiation is the energy emitted by matter in a form of electromagnetic waves, and this is as a result of the changes in electronic configuration of atoms or molecules. For this mechanism, we are not requiring presence of an intervening medium, and although it is a volumetric phenomenon, we mostly considering as a surface phenomenon where a solid is opaque to the thermal radiation. For this type of heat transfer, we can formulate this as Q radiation of a surface to ambient could be formalized by sigma, which is Stefan Boltzmann constant, and the other variable as emissivity of radiating surface, which varies between 0 and 1. Different material, they have different values. Cross-sectional area, again, it is normal to heat transfer direction. Temperature of surface in a power of 4, and temperature of ambient in a power of 4. So up to this point, we have summarized or let's say introduced these three heat transfer mechanism with their formula. One additional note about the radiation is that radiation heat transfer between two phases really depends on the shape of the phase, their orientation, and also the distance between them. And because of this reason, we are defining radiation view factor mostly in our calculation, which is a fraction of thermal energy leaving a surface of object 1 and reaching a surface of object 2, determined entirely on the geometrical consideration. Also, we will consider a multiplier to the radiation equation. It is unitless, and it's between 0 and 1. And the last note I would like to add here, for concave faces, they can radiate onto itself, but planar and convex faces, they don't have this ability based on the geometrical consideration. All right. That is bringing to our, let's say, end of theoretical and background, let's say, definition of heat transfer. Now we would like to practice this concept through a case study, which is the thermal analysis of a microchip. As you can see in a picture, this is a microchip we have. This is made of ceramic with some isolated conductor and a heat sink, where microchip generates 20 watts of heat power, and connectors are, let's say, insulated. In this case, we will have the case of steady-state heat transfer setup. Then we will consider a thermal, let's say, analysis, where we have a temperature distribution in first 300 seconds, and after the power is first turned on. Then we have a transient thermal analysis where this heat loading will be varied. It is increasing from 0 in first 30 seconds and turn off for the next 30 seconds. So the total time is 60. From 0 to 30 we have loading, and from 30 to 60 we have no loading. And the last case we will consider is transient thermal analysis, where the heat generation is controlled by a thermostat, and it's getting on and off based on some selection criteria. All right, so let's bring on the case study for you. Here is the case study, and this is our model. Okay, review the model. As you can see, we have connectors, 3 connectors. We have heat sink, and we have the microchip. Now, if you like to do a thermal analysis at any time, what you have to do is first go to your simulation tab ask for a new study, where this time you're asking for thermal analysis, and click OK. Same as the other simulation, let's say, options. You will get the simulation study tree here. The first option and the first thing you have to do is to define the material for all our part. As you can see, it's been all assigned here. Connectors are made of copper, heatsink is copper, and ceramic porcelain is the material for microchip. In the next stage, we have to specify the connection between the microchip and heatsink. This is available on contact set definition. By clicking on this, you have to select your face, and for the type you can say thermal resistance, bounded or isolated, and simply selecting your faces. This is what I've done before, and as you can see, we have defined this thermal resistance at back of the heat sink and top of microchip, where the value of thermal resistance being defined as 2.857 E-6. So this is the only connection we have, and thermal resistance is being fully defined here. Next step is to bring our thermal loads. So as it is a thermal study, this is not loads, this would be thermal loads, and right click, you can see you have the option of applying temperature, convection, heat flux, heat power, and radiation. So as we know, we have a heat power through the microchip. Therefore, if we select this face, we can apply 25 watts of power generation to this microchip easily. So make this configuration okay. Then we know that the whole surfaces of microchip and heatsink are exposed to the free air. Therefore, we are expecting the convection mechanism through these domains. But for the connectors, we have fully isolated section. So simply applying heat transfer convection option, and we're getting all the faces of the heatsink, where the H factor or H value is considered 250, and the bulk ambient temperature is considered 300 degree of Kelvin, which is 27 degrees of Celsius. Same as what we did here, we doing for microchip, selecting all the faces, putting the value of 100 for H and ambient temperature of 300 Kelvin. Okay, so apart from this, we can't see any other setting. So we put the heat generation, and we said what is the heat transfer coefficient convection is around this microchip and heatsink. Now we have to mesh and run the result, which I've done it for you. It takes some time to resolve. Now let's review what sort of result we get. The first standard result you get is thermal result, where we're talking about the temperature distribution. So you can see the maximum temperature is 179 Celsius, which is happening here on the top of the microchip, as we expecting. But sometimes it's very hard to decide about the temperature distribution when we have this 3D. You can always go and do the section clipping from any basement, could be front, top, or right plan, and make this happen on the center, going through different section of the material, or give it a angle in X and Y direction. This is the planar cut. You can have the option of cylindrical cut. Again, doing on different plans, making different decision, put it in a different locations, and make a specific, let's say, plot for yourself. But what we can see is the maximum temperature here. The other result option we have is resultant heat flux, where you can see in this specific case we have the maximum heat flux or heat transfer per unit area happening from this cutoff section. And also you can probe these values and get a better idea at any stage, where it is showing you the nodal value, the value at that location, where is the location, and depends on how many probing you have, you can get the average, maximum, minimum, and RMS. You can ask for the graph saying different nodes. This is how heat flux change. You can have a predefined spots where you do the graph for your heat flux at that specific location. Also, we can get some specific, let's say, graphs as well, where we're talking about least heat power. Then if we change these to watts, we can go at any surface like this and ask for heat transfer, heat power generation here. It's showing us no power in, power out is 0.06096 watts. Simply means over this surface, the net heat going out is 0.06 watts. If it is a plus, then it is heat coming into the system. So we can have specific, let's say, evaluation about our, let's say, heat transfer results. Now, what we have considered in this study is that the result of steady state thermal analysis, which we have just completed, describe the situation where sufficient time has elapsed and the heat flow has stabilized so that the temperature field reached the equilibrium. But the question is it the case that if we considering it, let's say, room temperature initially, and we turning on the heat generation of 25 watts, how long does it take to reach to that equilibrium state? What we resemble, what we simulated here, is that time is elapsed. Then we're saying, all right, everything is now being established as it is. Now I would like to see. But the question is never like that, because this microchip could be started from the temperature of the room, and by putting this heat generation, how much time required to reach the equilibrium. This is why we have to, let's say, define a transient analysis in real case value. Our objective is to monitor the temperature changes during the first 300 seconds of operation, with particular attention to the temperature of the middle connector. Therefore, we have to create a new study. That's what I've done here. When you do that, the first thing is to change the properties of this study to a transient analysis, just by right-click on study type, go to properties, and here is a new communication window. It's asking you the solution type, which is transient, or could be selected steady state. Then asking about the total time, where, as we said, the goal is to put the total time as 300, where time increment is simply 10 seconds. And we would like to see if we're starting from initial room temperature and adding the power of 25 watts, how long does it take to get stabilized and everything is not changing over the time. So also you can bring the fluid convection effects from SolidWorks flow simulation. Then there is no need to say what is the H factor. We simply doing this thermal analysis in a flow simulation, bring the result over the whole domain here by just ticking this and saying what is the result file. Then there is no definition of convection, which is more accurate and more, let's say, correct. But we accept it as it is, and we're clicking OK. So that is the first thing. Next is the same as contact, let's say, thermal analysis, the heatsink. Now we would like to introduce initial temperature of the assembly. That could be done by right-click and temperature, which I've done here. You can see if I go to edit definition, what I've said, all the components in the assembly are initially at 25 degrees of Celsius. Then from this point, I have applied the same thing to heat transfer convection mechanism and heat power. As you can see here, we have 25 watts on a microchip. We introduce also a control of some specific points for result review. For example, if we want to see the temperature change of that specific node here, a specific point here, then we can always go to evaluate and define a sensor. This sensor is using the simulation result, where about the data quality we can use thermal, and what we would like to trace could be temperature, resultant temperature gradient, or resultant heat flux, where we're simply choosing temperature. The unit for this sensor is Celsius, and if this is the sensor for the whole domain, where we have the result option, we can accept it as it is, the maximum temperature of the whole domain. But if we are interested, the maximum values of temperature at some specific point, then we have to use maximum over selected entities. Then we are able to go and pick the point, or pick the line, or pick the face, anything you like, and click OK. This will trace the simulation data of thermal, of temperature at that specific, let's say, point, where that is the maximum temperature happening there over the time. So clicking OK, you can see we have defined a new sensor here, a thermal transient sensor. All right. So by doing this, so we have fully controlled everything, and now we can ask for running simulation, where I've done, and here are the results, temperature, and I would like to bring a comparison of this transient study with our steady state study. Now have a look. Here is the steady state, and here is our transient result. You can see that steady state, where it's not considering any timing, it's showing the final temperature as 179.5 centigrade, and this is the same case after 300 seconds of transient analysis. So we can see that the transient analysis reached to the equilibrium point after 300 seconds. But the question is it really 300 seconds, or it is less than this? So means way earlier we have reached to equilibrium state. How we can check this? Let's get back and come to our result section. Transient. We can go to the result section and ask for graph transient sensor, where we can specify time and temperature, where I have created this case for you here. Now you can see that the temperature starts from what it was originally, and we simply specify that around the let's say room temperature. It's been raised up to this point where you can see that is maybe the point that we have less variation of the temperature in continue, and that is around 130 seconds. So such a system needs 130 seconds to establish the equilibrium state of the energy reaction heat transfer interaction. For the rest, it is simply steady state case where the temperature remains to its final value and remains there. Okay, so this is the main difference we have with steady state analysis, where we are not considering any initial condition such as temperature, to a transient where we have some initial condition, for example the room temperature, and we're reaching to the next equilibrium by applying heat flux, heat generation, heat power, or anything else. So this is the comparison, and this is how we can set up a transient and steady case. Now the question is, I would like to have a study where the heat loading is changing by let's say a curve. So simply duplicating this study, I would like to show you with the same condition as a transient let's say study. If you go to apply your heat power not as a constant value, you can always have a value which is dependent on a curve. So the nominal value is 25, the maximum value is 25, but if you click on that button, use time curve, and ask for edit, you will have a new communication window where it's asking about the timing and the percentage of the heat transfer nominal value. So what we specified, we said 0 second, 0 heat transfer. From 0 to 30, we have 100% value of heat generation there. So from 0 to 30 seconds, it will reach to its maximum value of 25. But from this point, 30 seconds to 60 seconds, it's getting turned off. So as you can see, it is decreasing. Any type of input heat transfer or heat load you would like, you can define it here. Since you have defined, you can click OK. The rest of the studies exactly look like what we done before, and then asking for mesh and run, and now you can see the thermal let's say result, where the temperature at the end is 26 degrees when we have a variation of load. And also because we had the sensor at that point, we can now trace this result and see how that specific point is changing. Now look, from around less than 40 degrees, it is rising and rising, and now look at this point. This is where the time is around 40 seconds, not 30 seconds. So we have turned off the heat generation at 30 seconds, but the system has its inertia to respond to that, let's say, power cutoff. The temperature is getting rise to 103 degrees on 40 seconds, and after 40 seconds, we have the decrease of the temperature over the whole time period. So any point, if you like, you can make a trace. Any sort of function you would like to define, then you can define it as an input parameter. But very important is to analyze and understand your result, that it is not happening at 30 degrees because we have a resistance of material to a sudden change. All right, let's bring on the other case scenario. If we would like to control periodically about the values of heat power into our system, we would like to keep the maximum operating temperature at the middle terminal below 120 degrees. To achieve this, the heat power generated by the microchip needs to be controlled. This can be simulated by the thermostat feature available in SolidWorks Simulation. So let's create a new study where I simply duplicated my transient 1 study here. Then everything is again the same thing except the heat power option. So if I click and ask for heat power, you can see I have to select microchip. For example, this not the face, the component. So say microchip. Oh, sorry. That would be very hard to select one by one, but we have to select this, the nominal value of 25, and then here is the option, thermostat transient. If you click on this, it will ask about the orientation, cutoff details. Now let me show you the one I have created here. So edit definition. So as you can see, this is what I've selected. The nominal value is 25 and there is no variation of the time for that one. So on this vertex, we would like to control that the temperature, if it's below 100 centigrade Celsius, the heat generation will turn on. If it's going over 120, that is cutting off. So this is the thermostat option. We set upper and lower limit. So the system is operative. Heat will generate between 100 and 120. And then beyond these points, we are just getting cut off. All right. Except this, the rest is the same. And we ask for run, which I've done. And then look at the temperatures. This is the temperature result. This is the thermal result of heat flux, where it's happening again at the cutoff sections. Now, if we would like to make a time history graphic transient sensor of a time and thermal and clicking OK, now you can see a very important fact here, that the temperature start rising to somewhere more than 120 degrees, which is 124, and that's where the thermostat acts. It dropped down to around 92, and when the thermostat reacts. So as you can see, the graph clearly illustrates how microchip heat power is controlled by thermostat. Because of the heat inertia, the temperatures oscillates between 92 and 125, even though we specified operating range between 100 and 120 centigrade. To keep the microchip temperature below 120 centigrade, as we originally intended, we would have to define the upper bound temperature in thermostat definition to below 120. The actual upper bound temperature could be found by try and error. So this is the option we have. However, we can't really control the reaction of our system due to the material inertial relief here. Therefore, if you are simply looking for this option, then you have to consider a more regular, let's say, a more try and error to find the exact bounding. So as a conclusion, guys, what we've done, we simply introduce how we do steady state. So simply steady state analysis is talking about the final situation or equilibrium situation where we simply ignoring the initial condition of our let's say model. So there is no time integration. So we're saying if we have a temperature like this, what on some specific phase, how it's getting distributed after it's getting to equilibrium, or if you have a heat flux or etc. But transient analysis will have an initial condition, a final condition, and any thermal loads, let's say, concerning. We can always modify our conditions by input conditions by their variation with time and their magnitude. So we can have a different load stepping, or at the end we can always control our let's say operation system by putting a thermostat option in this case. But what I would like to add, the main question here about this study is where I've put the convection coefficient film as a constant value. This is not a real case, and if your case study concerned about a very detailed and accurate measurement of this, you have to get this your model, put it in let's say a flow channel where it could be a zero velocity flow channel or a forced convection case, and do the thermal analysis on a flow simulation, get the temperature distribution over the whole phases there, and bring it to this study. Otherwise, whatever estimation you have, whatever let's say inaccuracy you're bringing on this type, then it will be there and your result would be off with that much. So we have to understand it from the beginning, and in most of the cases accurate results are simply requiring the convection coefficient factor to be estimated from the fluid analysis. All right, so that is concluding this session for us. Now, before I'm ending and going to your let's say question session, what I would like to present that with SolidWorks Premium, you're getting the static analysis and motion simulation option. But if you are interested in thermal analysis, as we presented here the case, SolidWorks Professional is the right license for you. You will also get the option of frequency optimization, drop tests, sub-modeling, 2D simplification, buckling, pressure vessels, and etc. But for those who are really dealing with the complex models such as nonlinear static or nonlinear dynamics or linear dynamics, SolidWorks Premium is the solution where you will have the fluid simulation as well as the other let's say options you have here. Note we have the seminar on 26, and this is my contact details. What I would like to ask now, if there is any question here in let's say chat box, and let me bring it out. Hang on, guys.